Sorry. No. So you can are you capturing audio, Tony?
I'm actually capturing through the mic at the vibratory bit, so I really don't need it. As long as he speaks loudly.
It's probably
Oh no, I've already made a deal where my logo will be. So that was not. Yep, thanks.
Yeah, we need to
Let's talk
take care of
about
that.
podcasting.
We need to take care of that.
Sorry. You all still interested? Yeah.
All right.
Forget where we left off.
Hi. Welcome. Hi. Hi. Thank you. I'm Mark. I'm the co-organizer of Stats Programming DC along with Julia. Here's Julia. So thanks folks for coming out tonight. We're going to have a pretty cool talk about deep learning. I know deep learning is really hot and cool and everybody wants to get to deep learning. So thanks for coming. There's plenty of food out there, so if you're still hungry, please help yourself. So let's see, what's the bulk party? So we have a smaller room, therefore that's why we had to cap the RSVPs. We still had a huge wait list. We had 200 RSVPs, so I was estimating about 100 people. This room holds 136, so we're at about 70 maybe? Okay, so it's a little less than we normally get. Which is why, if you RSVP, please come, because we seriously, like, we budget for food based on at least half of RSVPs, and if we get 100 RSVPs and 20 people show up and we have food for 100 people, guess what? There's a lot of waste there. And that's sponsorship money that we throw away. So please be conscious if you RSVP. If you're going to come, I mean, you RSVP, it doesn't cost anything. If you're not going to come, just change your RSVP. That's all we ask. So just please be conscious. Please tell your friends about this, because we normally get about 50% of attendees, because it's really easy to RSVP when you get the meetup announcement. And I get it, life gets in the way, you know, it's fine. But just if you know you're not coming, just change it so that we, your organizers, know, and we can plan enough in advance. So that's my PSA for tonight. All right. So as many of you know, we are part of Data Community DC. Raise your hand if this is your first time attending one of our events. Okay, welcome. No, it's not. No. So, for those that don't know us, we are Data Community DC. We are an organization that's dedicated to promoting the work of analytics and data science professionals around the DC metro area. We've been in existence since 2012. We have right now we have about 9 different programs under our umbrella. That's our list of programs: Data Science DC, Data Viz, Stats Programming, which is this, Data Education, Night Owls, Women Data Scientists, Data Wranglers, NOVA, Northern Virginia Data Science, and Full Stack Data Science. So check us out. All of our events are online on meetup.com. We have our website, datacommunityc.org. We have a newsletter. And you know, our reason for existence is to do this, is to provide learning opportunities, to provide networking opportunities, and have people come and learn and meet other folks, other like-minded data individuals. Let's see, okay. So, huge thanks to our sponsors. As I said before, a lot of what we do wouldn't be possible without our sponsors. You know, we have operating costs that we have to cover, but also mostly our hugest expense is food. And we do not charge for our events. We never have, probably never will, because that's just part of our mission. But, you know, we rely on sponsorship money to provide refreshments. We understand people come to our events after work and they're hungry. You know, sometimes we have nicer empanadas, sometimes we have pizza. So with more money, guess what? You get nicer food. If you have less money, guess what? You get Papa John's. Fair enough, right? So huge thanks for our sponsors. So AOL and Booz Allen Hamilton have been long-term supporters of Data Community DC. They're organizational sponsors. For full disclosure, I've worked for Booz Allen Hamilton. I've been with Booz Allen, but I've been doing this before. Who else from Booz is here tonight? Our speaker is from Booz tonight, and Julia is also from Booz. So who else is from here from Booz? Well, welcome, folks. Come to more events. And of course, so AOL and Booz Allen are at our kind of organizational layer. Huge thanks to GW and their MSBA program. We've had a long-term relationship with GW.
Don't forget O'Reilly.
I'm sorry, I didn't.
The slides. O'Reilly is one of our newest organizational sponsors. I apologize. And on that note, we have a bunch of O'Reilly swag here. We've got T-shirts, we've got stickers, we've got tchotchkes. Help yourselves. We do have a book for people though. This is for giveaway. This is for a raffle or some kind of giveaway. O'Reilly is also an organizational sponsor. Thank you, Mandy. This is Mandy. She's the president of Data Community DC.
Hey, everybody.
Hi,
That was pitiful. Hey, everybody.
Mandy. And she also runs Women Data Scientists DC as well. So check out her programs. They're awesome. She's awesome. We love you, Mandy. Microsoft has been a long-term sponsor as well for this particular program. And for those of you that are R users, those of you who have known me for a while, you know that the history of this group started as the R group, then we changed it to Stats Programming DC because we started doing a lot more Python. Before it was Revolution Analytics, which is now part of Microsoft. They offer a kind of an enterprise level R solution. So they've been a long-term sponsor as well for our group. So thanks to our sponsors for doing this, and we want to keep doing that. Okay, I'll skip that. Well, okay, I won't skip it. So again, call for sponsors, please, folks. We cannot do this without sponsorship money. If your organization wants to have your logo up there, if you want access to our 16,000 plus membership in the DC area, if you want to work with us for events, if you want to hire, if you want to get yourself in front of a great set of talented individuals in this DC area, come talk to us. We are very flexible. We will work with you, but you know, we certainly could use the money to keep running quality events. That's kind of what this is a self-fulfilling circle, right? If we have good events, guess what? More people come. If we have more people, we get more sponsors. If we get more sponsors, we get more food. And if we have great speakers and great food, guess what? We get more people. And we keep building the community, right? Yes? Yeah. Okay, good. So who here listens to NPR? Don't worry, I'm not going to ask for money, but please sponsor us. All right, we want you to talk. This is a community-run organization. This is a community-run group. The events that we do here are for you, and we want to rely on you not just to come, but also to share and talk. So this is just a laundry list of events or topics. For this particular group, we like to see code. So if you're doing stuff in R or Python or Julia or SAS, or basically if you are doing coding, if you want to talk about the work that you're doing, whether it's modeling, whether it's data munging, whether it's data viz, and of course there's going to be overlap with some of our other groups, but if you're an R junkie like I am, this is your place to be. If you're a Python junkie, I'm not a Python junkie yet, but it's okay. I'll get there. But seriously, so tonight's talk, we're going to have some Python code with TensorFlow, which is cool. But if you know of anybody, or if you can talk to any of the topics, again, this is just a laundry list. Suggest topics. We want to have events every month. So this is our July. So we had a special event about 2 weeks ago, which was a joint program with the STC. What Jared Lander talked about, R for Everything, which was a great event. This is this was our scheduled event. We have an event planned for August, which is Daniel Chen's going to be talking about R Markdown. He's a great speaker, really smart, really animated speaker, and it's a great presentation. So please come. We have a potential speaker, I think, for later in the year for October. So we can work with you. If you want to give a presentation, come see me, come see Julia, or Abhijit, who's not here tonight. So please, we welcome. If you're doing something cool, this is your forum. We want you to share your knowledge. Full stack agents. Sean, you're up.
Hi.
This is Sean. If you
Hi,
don't know.
Sean.
Hi, Sean.
Hi.
Hello.
Anybody fill?
Yeah.
Hi, Sean.
Oh, it's okay. We had them do it before. I have to do it twice. Anybody fill out that survey? It was at the bottom. It's supposed to be at the top. It's a Google form. I got a nod. Yes. I didn't know what there was a survey. I don't mean RSVP. I mean the Google form. I got a smile over there. Maybe he's just laughing at me. Only 1, 2, 3. Anybody else? No other surveys? So I'm playing around with this thing. One of the things, we have all these meetups as you showed earlier. And everybody wants to meet everybody. But who is out there and you ended up talking to your friends out there, and maybe you wanted to talk to somebody else, but you weren't sure, and then the event starts, right? come to the happy hour afterwards. There's a couple of matches here. We use the results of the surveys in order to match people based on their interests. So you kind of skip the whole, so what do you do? Right into like, oh, I hear you're into TensorFlow, right? Saves 10 minutes, at least. Gets rid of the DC initial thing. And in general, as we gather all this into a database, I think we've got hundreds of people that have done the in-depth survey, and that's Peter over there. Peter's helping me build the database. And we actually have thousands that have filled out these basic surveys, and we'll do some more follow-ups later on. If you want access to that database, that's what he was talking about with the sponsorship. There's a certain level of sponsorship. If you want to email us, it's just agents@Data Community.
Yeah, Sean is the he's our everything person. If you want to connect with anyone within the data community DC, Sean's your man.
I like to say I'm your window into the 20,000 plus data practitioners in the area.
So,
thanks.
Thank you. Okay, we've got two big announcements to make. So the first one is Data Community is putting together the first ever DC DataCon. Yay!
Oh, we're doing the matching with that too.
Yeah.
We're testing it here, so we do it better there.
Okay. You want to say a few words about DataCon?
Sure. So DC DataCon is our first conference ever. It's going to be awesome. October 3rd. The sign-up is already online. You can register. We have tiers for students and government employees to try and make sure that that's not a barrier. And it's accompanied by 2 different days with GW as well. A hackathon day and a training day. Should be amazing. I can't wait. You guys should all
We want to bring together, well, not we want to, we will bring together 1,000 people in this city to talk about, to geek out about data science. And it's going to be here at GW at the Martin Center, which is the student center. It's 2 blocks away from here on H Street. We have a full day's worth of programs. So the program is in process. So check out our website as it keeps new presentations keep getting added every day. People have asked me, are we doing a call for speakers or okay? So please check us out. So that's the first big event, and please go online. Please register. Please come. Please tell your friends. Second is O'Reilly is hosting JupyterCon, so it's I think their first ever conference just on Jupyter and the Jupyter Notebook ecosystem. It's in New York, right?
Yes.
And it's not here, but we have a discount because since they're a sponsor, they always give us discount. There is a 20% discount. What is it? UG
Data Science DC.
UG Data Sci DC. If you want to register with a 20% discount, you can use that discount code.
You can also use that discount code for Strata Hadoop as well. Also gets you 20% off.
For all, I think it's for all of the O'Reilly conferences or events. So that's in terms of announcements for SPDC. This, actually, let's see. Oh, we're missing a very important slide, which usually happens before announcements. So, what happens after we have our event? Yes! And what happens during data drinks?
Drinking.
Other than drinking.
Networking.
You meet interesting mentors and mentors.
No, it's called magic.
Oh.
The magic happens at data drinks. Okay? That's what happens. So,
all good deals in DC happen over beer or wine.
or some
cocktails.
alcoholic beverage of choice. So we don't have space reserved today, but if you want to stick around for data drinks, we go to Tonic afterwards. They have the 3rd floor blocked off today, so we'll go to the patio if it's not raining, and stick around if you want to. But seriously, like in all the years of doing this, like that's probably the highlight of the evening. I mean, not only the presentation and the speaker and what you learn, but it's also like who you meet, because afterwards you get a chance to talk to people in a more relaxed setting, a couple beers, and it's just, that's where the magic happens, seriously. So please stick around if you want to go to data drinks. And now this is your turn for announcements. If you're hiring, if you're running an event, if you have anything to share, this is your time to do it. So the floor is yours. Speak up.
Yeah, I work with a company on the West Coast in San Francisco, and we are looking at various people actually at various levels, so DevOps to back-end, front-end developer, and also machine learning, data science. So if you're interested, come talk to me afterwards.
What company?
It's they produce software for the pharmaceutical industry. I'm sure you have not heard about them. They're called collaborative drug discovery.
I'm a doctoral student. I study nurse. I'm a doctoral student at Madison University, and I focus on like measurement and intervention sciences, like human testing. Basically, I'm looking for consulting work. So if anybody has anything or knows of someone who's looking for someone to help with that kind of stuff.
You consider yourself a statistician?
Okay, statistician. I could pretty much do.
I got a couple hours for you, at least. It could turn into one.
Any other announcements?
Hi, my name is Heather Harris. I'm Casey, I'm a full stack open source web developer, WordPress and Drupal and such. I can pretty much do anything, consider myself a polyglot. Same deal, I'm a consultant, freelancer. Need help with anything? Okay.
My company is hiring. We are based out of Ruston. Company name is Crackle Industries, and we are doing hiring for DevOps and machine learning, artificial intelligence, and we talk about text processing, image processing, everything. We are doing a lot of things into cybersecurity, risk insurance, and finance domains, especially stocks. So if you want, you can actually look at crackleindustries.com and you should be able to.
For those of you folks that are hiring, that are looking for people, after the event, please stand over here so that folks can come and find you and you can exchange information. Anybody else? Going once? Going twice? Okay. Yeah.
Hey everyone, my name is Kunal. I am from GW only. I'm here for the first time, so thank you for this thing. Being here in the GW, I never knew what was even happening on a monthly basis. So I'm actually looking for jobs right now. I have more than 5 years of international experience working in business analytics and business intelligence. I am looking to get into product management or more advanced business analytics. So if you have any offer or any opportunities, please, I'll be saying hello. Thank you.
That's brave. And when folks stand up and say, hey folks, I'm looking, that's really brave, so appreciate that. And let's give them a round of applause because that really All right, so now on to the main program. Well, just quick, so Abhijit, Julia, myself, you know where to find us. Let's go. Please welcome Daewoo Chung. He's a fellow data scientist at Booz Allen, and he's going to talk to us tonight about text processing with the deep learning text processing work. Thank you. So please welcome.
So just want to gauge the room before I go into this presentation because there are 40 slides, more than 40 slides, and we're not going to have time to go over all of them. So how many of you are familiar with neural networks? Okay, cool. So when I say then neural networks, how many are familiar with like convolutional neural networks, recurrent neural networks, more advanced forms? Okay, cool. How many of you trained a neural network? Okay, good number. All right, and then one more thing is, how many are you familiar with reinforcement learning? Okay, cool, thank you. So this is deep reinforcement learning for text summarization. It's a mouthful, and it's because it is, and there's a lot of components that go into building a model for this. And so this image here is, we're going to go over it. This is the alignment from an input to an output for text summarization using attention. And we'll go into details about that if you're unfamiliar. So this confusion matrix is how do you align, right, the input which is on the right to the output which is on the top. So the overview, we're going to go over extractive versus abstractive text summarization. Then reinforcement learning. Shortly, we'll go a brief tour of neural networks, and then those for deep reinforcement learning. And then we'll go into deep reinforcement learning for text summarization. And then finally, we'll just do a very quick overview of TensorFlow's API for sequence-to-sequence models, which is the basis of this text summarization model. So we'll start with extractive versus abstractive text summarization. So extractive text summarization is quite straightforward. It's given this input of this text, right? Whether here I took this paragraph from TensorFlow's page and just produce some type of summary that is just straight copy and paste, right? So it finds either phrases and sentences in the input and concatenates them and then outputs that as a summary. There are many algorithms out there that are not deep learning based. Most of them for extractive text summarization aren't. And they do a reasonably good job on this. So this one, as you can see, it works reasonably well, but it doesn't have much character, right? Because it's just taking words straight from the input and creating some type of representation. But we know that as humans, when we try to summarize text, we add our own, right, our own flair, our own character to it. So then comes extractive text summarization. So this one, right? Now you're typically a neural network, will try to add its own character to it. So it takes this blurb about TensorFlow, and it outputs TensorFlow is awesome. This is actually a very hard problem because now it has to have some type of understanding of natural language. It has to be grammatical, it also has to be sensical, it can't just output all these random words. And that's what basically happens for most people who try to train an abstractive text summarization model. And as you can see that here, this is depicting an encoder-decoder framework or sequence-to-sequence model that we'll go over quickly later in the talk. But see, the green portion is the encoder. It creates some type of latent representation based on this text, and then the decoder creates this new representation, this generated output of this input. But again, abstractive text summarization is very hard. And especially early in your training process, and it depends if you actually have the resources. So this I would actually consider really good because you would have to, when you or a, right? It actually makes sense that it's outputting these words because it's just trying to guess how can I summarize this? I'm just going to summarize it with the most frequent words. But then as you can see, when you do have a model that is getting closer and closer to converge, it still has this problem of repeating the same phrases over and over again. So this is something that you'll see close to when you're seeing your model moving closer to convergence. So TensorFlow is awesome. The next thing is sometimes your outputs are nonsensical. And it outputs something that looks like a bag of words. So that if you were to reason about it, you can go I know what this output is trying to say, but it's not grammatical at all, right? Awesome, TensorFlow is the. And you'll see that this would probably be more so mid-stage of the process of your training of your neural network, that you're going to start seeing these bag of words that if you were to put them together would make a lot more sense. And then that shows that your model is doing something well or good. So we've gone through extractive and abstractive summarization. And sorry, I want to go over also in the bottom of these slides, right? I've provided links because I know that we're covering a lot of content, and I've kind of I've this curated list of what to go over if you want to get into depth. So here I found this this blog post from Jensen. I think a lot of you are familiar with. It's this Python library for natural language processing that has lots of cool algorithms built into it. They talk about doing extractive versus abstractive text summarization. They have a extractive text summarization algorithm built in, and they compare it to some other ones. But then they also compare it to trying to build their own extractive text summarization model. And they found out that so there's this open source code from the Google Brain team that you can train yourself on, but they found that if they actually wanted to train it to convergence, it would cost $30,000 in AWS credits. So, warning, yeah, it's deep learning, yeah, quite the computational resources and data. So, that being said, Rouge N. So, how do you quantify how well, how good your model is doing? So, it's there's Rouge N, there's Rouge L, Rouge S. We're just going to focus on Rouge N because most papers report on Rouge N. And it's very simple. I think most of you are familiar with like F1 score, and so that's what it is. It's just based on the precision, which is right the length of the intersection of your target, your gold standard output, and your generated output divided by the length of the reference or the gold standard input or output. And then the recall is the intersection divided by the length of the generated summary. And then your F1 is 2 times precision times recall divided by precision plus recall. So we're moving on to the next section. Any questions about extractive versus abstractive text summarization? It's rather straightforward though. Okay, cool. So we're going to go into reinforcement learning. I have to admit though, there's going to be a lot of slides on reinforcement learning, and once you find out how you incorporate reinforcement learning into your deep learning model, you're probably going to get a little mad at me. You're going to say, you went through all those slides and all it took was 1 line of code. Yes, but for the researchers to get to that point, it required this whole body of knowledge of reinforcement learning and why they chose this objective function that we're going to discuss at the end of the talk. So reinforcement learning is probably considered, when you first take a machine learning course, they're going to talk about unsupervised learning, supervised learning, and reinforcement learning. Rarely does the course cover reinforcement learning because they say that that's usually advanced, and because it is. It's quite complicated, and I highly recommend, right here on the bottom, there's a link to David Silver's course. He's the lead author of the AlphaGo paper. It's 10 lectures from his University of Oxford course, and it covers most of reinforcement learning, and it's just this is how I learned about it, and I highly recommend it. He's a great teacher. So what makes reinforcement learning so hard? So in your typical supervised learning fashion, let's say in computer vision, you input some type of image and your output, you have the supervised signal, cat or dog. In terms of reinforcement learning though, you don't have that supervised signal. It's based on this reward signal, a stochastic reward signal that is dependent on your inputs. What makes this even more difficult is that your reward is based on your actions. So this is non-IID data. So when you're working in a supervised realm, you're trying to train this on a data set that is IID. Here, you're working with non-IID data. And so since your actions affect your subsequent states, you have this process that you have to model these long-term dependencies, because in this picture here, in Atari, you make one move, and let's say in Atari, you move your joystick right. Your reward may be nothing because you didn't get killed, you didn't kill a space invader, so there's no reward. But all your actions, maybe 100 actions, will lead up to a reward where you actually kill a space invader. So how do you model that? How do you say that which of those 100 actions were the ones that led to that reward? And so there's this notion of a return or a discounted reward that comes into play, and how to model that adds to the difficulty of reinforcement learning. And so when you take when you learn about reinforcement learning, it's all about this Markov decision process. And it's based off the Markov assumption, and it's that the subsequent state is dependent only on the current state, And so in your typical model, it's very non-intuitive. If you think about it, you think you make all these actions, and all your actions are the ones that lead to this type of reward. But then in a Markov model, you're saying that your next state is only dependent on the previous state. And so that's what that top formula is. And then that G of t, that's a return. That is your function for the discounted reward. And the bottom is your representation of an MDP. So what is included in an MDP? S stands for your state space. So state space is, for an Atari, that's trying to model every single frame that you would get in an Atari game. Your A is your action space, so every choice that you can make on your joystick. P, that's your transition probability. So based on one state, what is the probability of a subsequent state? And is your reward function, and then gamma is your discounted factor. So in this model, you can see the brain, that is the agent. the brain receives type of state in Atari, right? You receive this frame from the game. Based on that state, you take an action, and that action gets fed into the Atari console, which is considered an environment, and this environment outputs a reward in state. And then it's this loop. It just goes over and over again as this agent learns this model of this environment. Any questions on this one? Because it's going to be, we're going to be building on top of this MDP. So the next thing is you have fully observable and partially observable Markov decision processes. And this is, it sounds complicated, but it's very simple. A fully observable model environment is like chess, where you see all the pieces on the board. So the actions that you make are in response to everything, right? That there is no hidden state in this environment. In a partially observable, something like Scrabble, there is something hidden from you, right? So the actions that you make are not all observable. That's why well-named, aptly named, fully observable and partially observable Markov decision processes. The ones that we're going to be going over, so like Atari is fully observable, including also in text summarization. This is going to be fully observable because we saw everything in the input, and now we're trying to generate an output based on that, right? The next thing is there are two methods to go about training your reinforcement learning algorithm. So there's this policy-based and value-based, and actor-critic is a mixture of policy and value. And you can think of this if you were given what is considered a known MDP. So that means you know all states, you know all actions, you know all rewards, and you know all transitions. Create a policy, right? So on the left, you see that once you have this known MDP, you can create a policy that you can give to an agent that can maximize its reward by going through, right, this MVP. And the policy-based method uses what's called policy iteration. This is for, that uses dynamic programming. But again, just stress, this is when you have a known MVP. Most of the time you're working with an unknown MVP. And then you have the value iteration that places a value on each state that you're in. And so there's usually this interaction in these methods of going from policy-based, where you use the value function, and then you correct it, you update the policy by doing some kind of greedy policy to maximize the value, and you do this back and forth, and that's how you create an optimal policy. In value iteration, you don't work with a policy, and you just try to maximize your reward. So in this case of a maze, the reward is every step you take is a negative reward. So your incentive is to finish this maze as fast as possible. And that's how, in this known MDP, you can get from the start to goal, and based on this policy, that's the fastest way to get there by maximizing your reward. And so here's just some more on policy and value iteration. So here we have policy iteration, where you start with this value function, right? And pi is your policy based on your policy. You evaluate it, you create the scores, which is on the right, right? You start with a 0 state, and then you place a value on every single state, and then you switch over to the policy, and then you create a new policy based on maximizing your return, and then you update your policy, and then you go back to the value function, and then evaluate the score for every single state, and it just goes back and back and forth until you reach convergence. This is again for a known MVP, and here are the functions. It's using what's called the Bellman equations. It's something that you'll come across a lot in reinforcement learning, and so V pi of S is equal to the expectation of the immediate reward plus the discounted reward of future values for each state. And then Q. So Q learning was also is a function. If you have the value function is just a sum of every action from a state, right? And so this is just another way to reason about it. And this was used. Q learning is DQN, which was the first paper like a few years ago that was released on how to play Atari games using convolutional neural networks and deep reinforcement learning. And we'll go a little more into detail about that. So reinforcement learning also has different ways to space. So again, I was emphasizing like that maze example, that's a known MDP. It's easy to reason about all states and all actions, right? Because you can only either go up, down, left, or right in that maze. And then we have only like 20 grids, so it's really easy to model the state and action space. But then if you're playing like a game like Go, and in the algorithm AlphaGo, you have 10 to the 170 states and actions. So that state space, there's no way that you can explore that or even have a model to represent that. And so there are usually different methods to explore and approximate your value function or your policy by either using Monte Carlo, temporal difference, and dynamic programming. So dynamic programming, again, is for a known MDP, but an unknown MDP, what you do to update your value function is, say for Monte Carlo, what happens is it needs to be in an episodic environment. So what that means is, given the state, play based on your policy, all the way to the end until you get to a terminal state. So once you get to a terminal state, then you can update V of S. And you do this over and over again, and this is based on the empirical mean for that value function. And one advantage of using Monte Carlo reinforcement learning is that it is an unbiased estimator. And so when I say unbiased, is because it actually is playing out and getting the actual value for, given this state, all the way to the terminal state. So temporal difference learning is now an online algorithm, but it's considered high bias because you're updating a guess toward a guess. And so given some state, you are updating this state just based on the following state that you get by taking an action, right? And so this one works in environments that are non-episodic, right? You don't need to reach a terminal state to update your value function. And so you can see that the advantages of this, it actually has lower variance because it's only updating based on one action, whereas in Monte Carlo, you have high variance because every time you start from one state and you do what is called a rollout, you end up in many different terminal states, and you have this high variance of your reward function. Then now you have Monte Carlo and temporal difference. So temporal difference 0 is what's depicted over there. And then if you go all the way, if you do TD learning to the final state, that is Monte Carlo learning. And so there's another algorithm that's introduced called TD lambda. And TD lambda is a weighted version of TD all the way up to Monte Carlo, right? So it's going through all the states and then doing a weighted function of all the updates that you could possibly make. Yeah, I hope that's a mouthful. So we move on to value function approximation. So again, yeah, this value function is very complex. What it's trying to do is how do you evaluate a state, right? And this is now currently done usually with neural networks because, right, if you have this known MDP, usually that you don't need to use a neural network, but when you have this large search space and you're trying to model these really complex dynamics, that's when neural networks come into play. And so there's this value function approximation, and one of the top methods is called SARSA, right? And it just means that you have this state action, right? And based on the state action, you get this reward. You move to some new state, and then now you take right, a selection of one of another actions. And that is the Q-learning update algorithm for the deep Q-learning network. And so it's whatever the current value for the Q value is for a state action pair plus a hyperparameter alpha, and then it just tries to minimize, it becomes like a regression problem of the reward that you got plus the expected reward for the next step minus whatever you thought the current value of this state action pair was, right? And then on the right you have is the Monte Carlo tree search algorithm, which was also used in AlphaGo, and this is how you approximate the value function, where since you have this large search space, you want to prune it, you want to cut it down. It uses beam search and does the Monte Carlo search rollouts. and it updates its current state by first doing the Monte Carlo rollout, going all the way to the terminal state, finding out the reward, and then updating a set of nodes. And based on those nodes that it updates, it moves down and it decreases the number of nodes to explore, right? That's what beam search is. And then it uses some type of default policy to evaluate everything else in the rollout. So that's value function approximation. So the DQN paper was based on Q-learning, which is a value function approximator. But then most reinforcement learning methods now have moved on to policy gradients. And policy gradients are a little more intuitive. Given some input, it creates a distribution over actions, right? And it's based on this policy function score gradient. And it's right when you are trying to maximize some type of reward, and this reward is represented as f of x in this slide. It's just the definition of the expectation, right? And you go through the gradient of the expectation is, right, the gradient of the sum of the probability times the function, the reward function. You swap the sum and the gradient, and then you just do some algebra by just multiplying and dividing by p of x. And then you use the fact that, right, the gradient of the log of z equals the gradient of z over z. And again, you come back to the expectation. So, I mean, these are equivalent, but then using this new representation of the expectation, that's when policy gradients come into play. And you're like, okay, I see all this math. I don't understand, why is this useful for me? So f of x, again, that's your reward function, right? Your reward function for a state. So if we go back to the example of like text summarization, you generate a summary and you get your Rouge score, and that is your f of x. But then, based on however your model performed, you want to make sure that the next time it sees the same input, it wants to output more probable words, right? It wants to maximize likelihood. And so that is, right, log p of x. The gradient of log p of x is your input. And so using this function, you want to make sure if it's a positive reward, that the next time you see that input, you want to generate output that has high log probability, right? And to do that, here's something that's a little more intuitive for the policy gradient function score gradient, is you have these dots on the left of this Gaussian distribution, right? And you're trying to model this density function. And in the green, you have these examples that have high reward, and in the red, you have examples that have low reward. And so what you're trying to do, based on the previous equation, is you're trying to tug this density function to output more or examples that have higher reward, right? And that's how you see that after this parameter update, you get that picture on the right. So, are there any questions on this? I hope that wasn't too much of a mouthful, but it's very important that this is well understood to understand the objective function at the end of the talk. Yes?
Right, I don't understand this graph.
Yeah.
Can you go over that?
Yeah. So let's say we just, on the left, we just put some points, right, on this. And this it was distributed by some Gaussian, right? And then let's say for like this example, right, once you, a better way to think about it is, okay, let's go back to Atari, because I think that's easier. I hope this is a good way to frame things. So let's say, based on some action, right, you had a +1 reward from this action, +1 reward from this action, +1, and let's say, we're thinking of in continuous space. So I know this isn't discrete, but, and then all the red ones are the ones that led to, right, negative rewards. And so what we're trying to do is that the next time it sees, well, in Atari, that frame, it wants to make sure that it outputs actions that are going to produce higher results, right? So it's going to shift the distribution of its weights so that the next time it sees its positive rewards, that it's going to output those actions that lead to higher rewards. And so the ones that lead to negative rewards, it's going to de-emphasize those. Is that a little better? Oh, yeah.
So how does it matter, right? When the gradient can be calculated by the gradient of log of x. I just don't see why the gradient of log of x is like this.
Right.
Yeah.
Okay.
Yeah.
So usually when you're building a model, and you're trying to maximize likelihood, right? And so that's what, in your typical supervised sense, that would be your objective. But then we're adding this extra one, right? This what is often called the advantage. And we're adding this reward. And since you have this stochastic policy, since you don't actually have a supervised learning objective, you need to use this reward function to influence the way how you update your gradients. Because you don't have something like, this is not some input of an image and you know that it should be cat or you know it should be dog. And so this is actually, you can think of it as like a trick of saying that since this, the action that this output had negative effect, then we want to make sure that the density function will understand that, right? We want to make sure that the weights will influence that to move away from that action that we took, right? And then it also, if it was a positive one, we want to shift the weights of the distribution so that we have a higher likelihood of reproducing those actions. And yeah, I don't know if that helped at all.
Just use the cat dog example. So you didn't have the tags on those images. What would your reinforcement function look like so that way you could train a model to recognize cat versus dog?
Yeah. So not sure, I've never thought about that. But the tricky thing about reinforcement learning too, and I failed to mention earlier, is that this reward function is, unless you're working in the realm of Atari where it's straightforward, right? You have these points, and it's easier to understand how that reward function works. But in terms of something like robot manipulation, right? You have to define these arbitrary reward functions. So you have to place a value. And that's what a lot of people have criticized reinforcement learning methods, because humans are just placing these arbitrary values to certain actions and then training their algorithms. So in terms of your example, I would assume that if you wanted to train something like that for reinforcement learning, you would have to provide your own reward function and define how that would work and the interaction of it with the environment.
What reward functions have you worked with, and how do they relate to it? You might understand.
Yeah, so in Atari, right, you get this, it makes a lot more sense because every time you make some type of action, you kill a space invader and you get 5 points, then you can use that as, right, that's your f of x. And then your log p of x is your input image and your action that you output, right? And so that it knows that the next time, if you had a high score based on the action that you took, given that input, it's going to make sure that it reproduces that action. But if it saw that you were killed by a space invader, it's going to make sure that it avoids that action the next time it sees it.
Is choosing your reward function equivalent to having labeled data in some sense?
Not necessarily, because labeled data, right? If you wanted to label your data, like let's say you had 1,000 images, you'd have to go through every single image and label it, right? In reinforcement learning, we're mostly talking about what is called model-free, where you don't have a representation of your model, this transition reward, because Atari, when you're working with an Atari console, right? It's a model-free reinforcement learning because the console is giving you the next state, and it's also giving you your reward. So you don't actually have to label anything, right? And so there's also model-based reinforcement learning where you try to actually create your own representation of what you think the next state reward pair would be.
So I assume that the f of x here is the reward function, right?
Sorry?
The f of x here is a reward function.
Yes, yeah, the f of x is a reward function.
Okay, so so we want to maximize the reward function.
Yeah,
Right?
yeah.
Okay. So if that reward is positive, so by looking at this, like log p of x is always negative, right? Because p of x is it's always between 0 and 1. So if f of x, if we want positive, and then when we calculate this gradient, and then this gradient will be negative, then we cannot maximize the.
Well, then you can just put a negative sign in front of it.
Okay.
Yeah.
Okay, I see. Okay, I see.
Any other questions? Oh, we are. Okay. And so it's 8 o'clock and we're not as far as I would like to be. Epsilon greedy policies. What is this? So if you try to maximize some type of function based on some greedy policy and you haven't explored the state space, you're going to converge to something that's really bad. And so most reinforcement learning algorithms introduce this epsilon greedy policy where just based on some hyperparameter epsilon, if it is one, it either selects the action that maximizes the queue, or it just takes some random action. And so this way you can explore your state space more effectively. Since it seemed like most people are familiar with neural networks, we're going to breeze through these slides. Here is your feed-forward neural network. This is something that I wanted to focus on. So a lot of people think that if you want to build something state-of-the-art, it has to be a convolutional neural network or a recurrent neural network. Google just released this paper like in the last month. It's called Attention is All You Need, and it's just a feed-forward neural network with attention. And we're going to go a little more in detail about what attention is, if you're unfamiliar. I mean, it's a little more than just a feed-forward neural network, but it's not using convolution. It's not using recurrent neural network or recurrent cell. And so a lot of people thought, I mean, they report that it's much faster and that is kind of like a breakthrough. And this was used for a machine translation, and they reported state-of-the-art results, which a lot of people are recently, though. So convolutional neural network, I think a lot of people are familiar with this. Instead of having this dense a set of weights in between layers, it has sets of these really small weights, typically 3 by 3, what are called kernels or filters. Here's a great depiction that I got from Apple on performing convolution on your input, which is, you can think of it as like an image, and then you have this one filter, this 3 by 3 filter, and then you apply it over the entire image, and you get this new feature representation. One thing to note is that when people think of convolutional networks, they usually think of computer vision, but then a lot of work in the last 3 or 4 years has been done to incorporate convolutional neural networks for natural language processing. And something that I highly recommend you look into. This was released I think 3 months ago, and it's a fully convolutional neural network by Facebook Research, and they also reported state-of-the-art results on machine translation. But the cool thing about that is that, this is, I consider it a breakthrough because they're reporting state-of-the-art for ConvNet, not just using a ConvNet for natural language processing. And they're also leveraging word embeddings, which we'll quickly go over because now these word embeddings are these dense vector representations of words instead of these one-hot encodings, which was typically done before. Recurrent neural networks, these are closer to feed-forward neural networks, except that you have this time component, and that you have these hidden representations that work as a memory that is shared between each step. And so here is on the left a depiction of a recurrent neural network, and if you unroll it and how the hidden states are shared across the time steps. Here is now, that's a vanilla recurrent neural network that's rarely used in practice or if ever anymore. It's long short-term memory and gated recurrent units. These are a little more complex, and the big idea here is that they have this gating mechanism, and this gating mechanism adds to what is called this memory, and also removes stuff from the memory and passes that on to subsequent calculations. Okay. Now, making your models interpretable. I have a post to the effectiveness of RNN from Andrew Karpathy. I think a lot of you are familiar with his work. He's amazing. He's now at Tesla. He was at OpenAI before. And this is to make, right, a lot of people say that deep learning is non-interpretable. And here is this visualization library that he open sourced to show how to make RNNs or deep learning more interpretable. And you can see that he trained this RNN, and there was he observed one of the activations of one hidden unit, and he saw that this hidden unit got excited or was activated whenever it was ever in between quotation marks. So that was really cool to see that. And he has more examples on his blog. You can take a look at it later and read through. It's a wonderful post. But then you can see, right, when people say deep learning is non-interpretable, you can't use it. I say otherwise. Okay. Although in practice, you really now see just these vanilla recurrent neural networks. You see bidirectional recurrent neural networks. And so the idea here is that you have a LSTM or gated recurrent unit going from left to right, and then also right to left. And here is this code snippet. Let's talk about this really quickly. Does anyone have a question about this? Because I think this can get a little confusing if we move over this, because this is usually a component of a state-of-the-art recurrent neural network. And the motivation first behind this was from a machine translation, that they found out that after you encoded, you had this hidden representation of some type of your input sentence, and you output this target representation. So let's say you're going from English to French. They found out that it worked better if you actually flip the words in the input when you're trying to generate the output. And then some guy got really clever and said, why not just create representations of going from left to right and right to left, and then using that as your representation, and they found out that that got state-of-the-art results.
Is it similar to, instead of just trying to figure out what's probably next, you're also trying to figure out probably beforehand?
Yes. So it's this memory in a recurrent neural network, and especially these LSTMs or gated recurrent units, they're storing this, what is called like a short-term memory or long short-term memory. And so when you have this word embedding, right, you can think of it as, let's say, the representation for the word, I don't know, desk, it looks like kind of like this, right? And that's getting passed on. So that would be passed on to subsequent, right, computations, so that when it sees something like that, it's like, oh, that looks like desk, right? So that the network knows that it saw the word desk or any other words, but then it builds its representation because it's actually looking at several words over this sequence. And I hope that kind of makes sense. All right, so bidirectional RNNs may sound scary, but in TensorFlow, they abstract a lot of this and make it a lot easier to use. There will be reference code posted to GitHub. And if you want to do this in TensorFlow, you would just write bidirectional dynamic RNN. You have to declare your forward network, right? And then your backward network. And then you have your inputs, your X inputs, your sequence links. So RNNs are typically much slower than convolutional neural networks because you have to do sequential processing, right? They're highly dependent on the previous inputs, whereas in convolutional neural networks, they're parallelizable, and that's why they're so fast. So this is one of the drawbacks of recurrent neural networks, and that's why they take much longer to train. But then you can have these types of representations of them, which have been highly useful for natural language processing. But again, TensorFlow, even though it's easy to get to this state, building TensorFlow models are quite complex if you have worked within this library. Okay, sequence-to-sequence models, I think we've covered them enough. You just have this encoder. You get a hidden representation of every single token that you've seen, and then you output right in your decoder network based on all of the inputs that you've created these hidden representations for. All right. This again is a slide on word and character embeddings, and if you are new to it, they just have these interesting, these dense, low-dimensional vector representations of words, so that you can have interesting linear relationships and other properties that have been using for deep learning in natural language processing. The bottom is how one learning objective for a word embedding model, right? It's a 3-layer neural network, and so your inputs, so if you have, it has this notion of a context, let's say you had 5 words, the middle word would be the target, and then the surrounding words would be your input. And so given your surrounding words, can you guess the output, the target word, the word in the middle? And so this is called the continuous bag of words model. There's also other approaches. That was the word embedding model called Word2Vec, was originally introduced by Tomas Mikolov when he was at Google. He's now at Facebook, and he just has a new open source called Fast Text. And I highly recommend this because the Word2Vec model would take days and days for you to train, but then this Fast Text actually trains reasonably fast on a CPU, so you don't need a GPU, which is quite cool. I highly recommend to check that out. And then on the right, just show that, yes, you can also have, since you have these word embeddings or character embeddings, you can now put them through a convolutional neural network. Okay. And then all these neural networks are trained by backpropagation. Yes. So deep reinforcement learning. Okay, now we're getting close to the end. We're trying to put everything together. DQN. Here, just this Q learning, that Q, the value function approximation that we've gone over. AlphaGo, here is something that actually uses policy gradients. So it used that objective function of the function score gradient. And to me, this was just like one of the most fascinating papers I've ever read when it came out. And I just love talking about it, but I guess it's not really applicable, but I highly recommend to go over it. And it uses, right, everything that we talked about in reinforcement learning. This was actually published by David Silver, so you can actually learn from the guy who was the lead author in this paper and is now trying to apply like deep reinforcement learning to everything in London. So it's based on supervised learning and then policy networks and a value network. And yeah, more details in the paper. So deep reinforcement learning, if you want to know what are the state-of-the-art algorithms out there, all these are open source, so it's great. So if you want to try some of these out, you can go home and look one of these up. A3C, asynchronous, advantage, actor critic. So that function score that we talked about, it's often called an advantage function. And so actor critic means that you're modeling a value and a policy function. And so here it's depicted on the left where you have you train several models, and you have this global model. These local models update this global model, and you go back and forth, and you can see that you have this you have the same parameters to output a policy and a value function. You have ACER, which is actor critic, which is another value policy function neural network. And ER is experience replay. So what they found is that what helps to lighten the burden on the environment, they actually create their own environment too by saving some of the actions that it gets from the environment and then training on previous state reward pairs. And so that's ACER, that's DeepMind, and that's also the ones who came up with DQN. Then you have TRPO, and TRPO is Trust Region Policy Optimization. The main thing about this is it adds this KL divergence term, so when it's updating the policy, it limits the update of the policy from the new policy from the previous policy. And that's like the big thing about that. And then PPO, which is the result of the image that I shared here, which is also open source and from OpenAI, is that they say that it's simpler than all these methods. This just came out 1 week ago, and they have a trained model online too. Okay. OpenAI Universe is something else. You can just test out your reinforcement learning algorithms and see how they do in a bunch of environments. It's actually really easy to do. It's really cool. Okay. So attention for sequence-to-sequence models. Let's see. I have okay. About to run out of battery. Anyone have any questions? We're going really, really fast now. Okay. So attention. So this is big. I don't read any natural language processing papers with deep learning that doesn't have incorporated attention. So I think this is kind of like the big one to think about if you want to build something yourself. And so the big idea here is that you have this encoder, right? let's say you have 10 words in your sentence, your encoder is going to create 10 hidden representations of that sentence, right? Then when it comes to your decoder, it is going to use those hidden representations from the encoder to generate a new word from the decoder, right? And how does it do that? It uses this mechanism called attention. And so here is just kind of, you want to just wrap your head around how that works, but we'll go into more detail. There are two different types, hard versus soft attention. Hard attention is using reinforcement learning. And on the bottom, you can see that's using hard attention. It's not actually that useful, but it's apparently according to this paper called Show, Attend, and Tell. But then you have soft attention, which is, it has to look, so these hidden representations are considered memory, right? Because it's previous input that you've already seen, and now you want to reason about them. And so when your decoder creates this new hidden representation, that's called a query vector in many papers. And you take this query and you go to your memory and you try to reason about like which word, which vector or which word from my input is most relevant for generating this output, right? And when you do soft attention, you actually do this weighted sum of all the hidden representations. So you can think of it as like in RAM, if you're trying to do soft attention, and you're trying to create what is like a neural Turing machine or differentiable neural computer, which we'll go over, which are more advanced forms, you have to touch every spot in memory to generate some type of output, and that's a very expensive computation. But then it's a lot easier to implement because if you try to do hard attention, you have to introduce this other reinforcement learning algorithm component. So here is something from more advanced forms of using attention, where you have a neural Turing machine and differential neural computer from DeepMind, and this is expanding that memory space to model, right, to have actually like a bigger capacity. So you can think of it as like Wikipedia, right? When you ask a question to this model, or let's say you're generating some type of input-output, it's only doing it based on that input, right? But if you wanted to create some type of representation that would persist and move on beyond that, you'd have to move on to something like, right, this a bigger memory. That's something that has a larger capacity. So you're not just reasoning over your inputs, you're reasoning over this huge corpus, or you're reasoning over your brain, right? Your kind of this whole knowledge of like Wikipedia to answer some type of question. So highly recommend to look into this if you're interested in getting, especially these are used for question answering models. So the attention formula, here it is. Again, it's a weighted, for soft attention, it's a weighted summation of all your hidden representations. So there are two main ones, Lual and Bodenau. Both of these, you can choose from both of them in TensorFlow. And so here you have the attention weights, right? You first calculate this like distribution over all your hidden states, and then you do that weighted sum based on that distribution, and then you perform, right, you create the final representation using attention vector. And so you can see how Luong does it, how Bodenau does it, and here is the next slide for encoder-decoder alignments. You can see how this is from machine translation, how you have this confusion matrix to compare from the input to the output. You also have this for text summarization. You can see right, how words from one language to the other align with each other. And you can see that, is your attention actually doing something interesting? How is it beneficial? And this is just a great way to take a look at it and understand the importance of attention.
Can you go back to the last slide?
This one.
No. Next one. So I understand the translation, but can you speak to the right side of the slide from terrorism to against? How is that? So your output over here against is essentially it's a relationship between two words, or is it the global terrorism, etc.? Is that just to represent the whole sentence over there? Is it representing a group? What is the representation on the right?
Yeah. So this is just more like to help you, because yeah, sometimes they're more straightforward when you're like aligning, right, economic with economic here, but this is just kind of like a confusion matrix, just saying that when it was trying to generate right, this word terrorism, right, it was looking well, so when it generated terrorism, it was actually only looking at terrorism and a little bit of Ivanhoe, right?
It's essentially replacing a sentence with keywords again, and not keywords, but
So
if
yeah.
you want to do this for a paragraph. I'm trying to think about the first slide that you showed about TensorFlow is awesome, right?
Yeah. Yeah.
So that's a whole paragraph against 3 words versus over here you have 10 versus 7 versus
Yeah,
15.
yeah.
What's the lift over here, I guess?
To what do you?
What do you gain from this? You had a sentence call, and you output a pressure calls for joint fraud. It's not really summarizing it.
Yeah. Oh, so this is just based on. I mean, I just took this graphic from a
Okay.
paper from Facebook.
Okay.
Yeah. So yeah.
All right.
So attention in TensorFlow. I want to say that this was actually just introduced, and it was a surprise to me. So I had to update a lot of my code. This was released like a month ago, and these are great improvements because it makes it much easier to work with attention mechanisms for training your models. So you can see before you had this monolithic function that had to define everything that you wanted to do with attention, but now and it was a bit of a black box, but now in TensorFlow you can actually select Luol attention, and then you pass your inputs, and then based on that it has this attention wrapper so that you can pass on to your decoder network. And so it makes it just much simpler, and the APIs are great, they're detailed, and they'll let you know, and also different types of parameters that you can select because Luol and attention, you can actually have their different variants, and they let you select among those too. And so this step is done in between an encoder, decoder, and TensorFlow. And I'll just show you quickly what it looked like before. And this is what I had to update. As you can see, it was not as intuitive, and it just kind of was like a black box. You just had this function called prepare attention, and it basically kind of did everything for you, and you didn't really know what it was doing. Whereas, before now, you first select your attention mechanism and you can pass it in. So they've done, it's quite a good upgrade to working with attention. And so then when you pass your decoder networks, especially when you're trying to generate a summary, so let's say when you're training, you know exactly what you want the output to be, right? Because you have this gold standard. But then when you're at test time, you want to add that character, that flair. So in TensorFlow, they have this basic decoder, and you use the basic decoder when you're training your algorithm, but then they have different methods when you're trying to, at test time. They have what's called like greedy encoder, all these other different types of decoder, so that can add some flair, some randomness, so it can generate different words, right? And so that's a new addition too that they introduced like a month ago, and that's really cool because now you don't have to define your own function to sample from your action space, which is something that I had to do. I wrote like a month ago. Yes.
Is it common to have an attention wrapper on both encoder and decoder?
Attention wrapper. So yeah, encoder.
It's usually done on both.
No. So the attention is just, you're wrapping it over on your inputs because, no, I take that back. Because the deep reinforcement learning for text summarization, it actually does it for encoder and decoder. So we'll get to that.
But so you're saying the more common is usually just on the encoder?
Yes, yeah. Well, we'll see because since they're reporting, the MetaMind team reported state-of-the-art results, and this was the first time people saw using attention in the decoder. We may see it a lot more now, right? That was a great question. Another cool thing, so a lot of people, when they think of attention, it's usually used in natural language processing tasks, but you can actually use it for just image generation. So this is just based on a paper from DeepMind where they used hard attention to learn how to draw. It's really cool using recurrent neural networks. So something I just recommend, kind of fun. All right, so deep reinforcement learning, we're wrapping it up finally for text summarization. And this is where I'm going to say that some of you may be upset that we went through all this formalism just to get to this point for this one little line of code. And So your encoder-decoder network has this local supervision, right? Because you have this gold standard summary, and so every time it outputs something in the decoder, it can compare it to the gold standard. So that is called local supervision. But then you also have this global reward, right? So global reward, we use the rouge and function to declare the global reward. So after it has generated the summary, we compare that our advantage or our reward function is the rouge score, right, of that generated output. And then you compare that to the gold standard. And so here is another way to think about it in a reinforcement learning sense. Right? You have this model, it generates the summary, it compares from the ground truth to its generated. You have this reward, and then you update the model, and you just go through this over and over again, right? And possibly, depending if you want to have like a really good model, it probably goes on for weeks. Well, if you want to have like a really good model that can cover lots of, if you, let's say you wanted to build something for like Wikipedia, yes, it would take about a couple of weeks. So, yes, we did all this just to get to here, this objective function, right? We're going back to this function score gradient and using that formulas that we used before, and this is what they introduce, and this is the reinforcement learning objective that makes their model perform the state of the art. And so first, right, you have your typical likelihood model, and then that's the typical maximum likelihood objective that you'd have in a supervised learning algorithm. And then you have this this reinforcement learning one. And so this R of y hat minus R of ys, that's just comparing, that's your advantage function, your reward function, comparing from the ground truth to the generated output, and that is, right, multiplied or against the sum of the likelihood of the generated output, right? And so you combine these objectives into this mixed objective of this supervised reinforcement learning objective, and that is really what turns a sequence-to-sequence model into a deep reinforcement learning model. And so here's some results. And they reported some results on this article. I mean, they have this, and you guys can take a look at a little later how it does. And yeah, it's quite impressive what they're doing. There are lots of tricks to this model, though, that considered hacks. So again, these text summarization models tend to repeat themselves. So one thing that they did is that based on the generated output, after 2 words, if trigram, right, 3 words have already appeared in the generated summary, then it will actually avoid that and then start over from scratch. It'll make the generated output select another word because it's trying to avoid repeated phrases. And so that's one way to add also more character to your outputs. They have all these other little interesting little hacks but it's basically a encoder decoder and also with attention on the decoder, and then also introducing this reinforcement learning objective. And then finally, TensorFlow API for sequence-to-sequence models. Again, a lot more robust, a lot more documentation. When I wrote it last time, I mean, you can go on TensorFlow API and see all this. There wasn't an API. So I was digging through source code, going through lots of forums, and just asking people like, how do I do this? I want to do this in a simple fashion, because one thing to know about TensorFlow is that, yes, you can try to be a hero and implement, because they have all the primitives for you to build your neural networks yourself. And that's what I did, and that's how I learned, but I realized once I started using their helper functions and I started understanding their API, my models trained much faster. So one thing is, like, when I was trying to create like the cross entropy error for a chatbot, I think some of you were at that talk when I did about chatbots. When I created my own cross entropy function, I thought was reasonably fast. I was like, oh, I mean, this is doing what I wanted to do. And then I came across this, when I was looking through the API, I saw that there is this like cross entropy for sparse like vectors with logits or something. And that's what it's called. And I was like, oh, you know, may as well use it. It's much cleaner. And it actually made my code 10 times faster. And I was so frustrated that I just didn't know about it earlier. Yes?
When you wrote yours, what language was it?
Oh no, so it was still using TensorFlow, but it was using primitives. Because right, you can declare these.
You can connect TensorFlow to another language so it runs faster. So would you write your algorithm in like Python and then?
Yeah. So.
Right. So is the other are the primitives written?
Oh no. Okay. I guess that's ambiguous. So Python has two, right? Well, no, it's expanded to other ones, but they're considered experimental. But they have bindings for Python and C++ and C. And when you create, they go out of their way to introduce this idea of like a graph, right? And you computation graph. It doesn't run until you call run on this session. And the reason they do that is that once you build your graph, and you have declared all your computations and everything you want your neural network to do, it actually delegates to C and C++. And so that's how it gets really fast. And so when I say primitives, I mean that I'm still writing Python, but I was declaring these matrices and doing the matrix multiplication myself, right? Because there's like this function called matmul, and that's how you multiply two matrices. And so you're using that like on this level where you're not abstracting anything at all, right? So it's just a very linear way to think about it. You're like, okay, I know exactly what my model's doing. That the output of this is the multiplication of these two matrices, right? Instead of using a function that's just called like, right, sparse cross entropy with logits or something, and where it kind of does like 3 or 4 lines of code kind of automatically. Yeah.
So what you mean is that these functions actually has incorporated all the primitives that wanted to.
Yeah, so, and it's not only that, the primitives, but it's actually probably just, I mean, it's a direct binding to like C, C++, and that's why it's going to be much faster. Whereas when I was trying to do it, well, I think the big thing with the sparse cross entropy is because I was trying to calculate, I was passing in these one-hot vectors from these large vocabularies, and so I was unnecessarily performing this large matrix multiplication when there are other more efficient ways to perform or to calculate the cross entropy. And so that's why they went out of their way to create that function so you wouldn't make that mistake and that the computation would be much faster.
I have a question.
Yeah.
You may be too young to remember, but there's a product or a service called Sumly that Yahoo bought.
Yeah.
Machine learning was probably, as we know it now, in its infancy. How does this compare to Sumly? That's the first question.
Yeah.
And the second question is, are there any off-the-shelf services out there with APIs that a regular Joe like me can use in that to do some of the same stuff that you're doing in TensorFlow and R?
Yeah.
So Sumly is the first question.
Yeah.
Because that I don't think that was machine learning like we know it today.
Yeah, probably not as we know it now. My guess is that it was using extractive summarization, right? So I don't, you know, I'm not too familiar with it.
You're probably still in high school.
But in terms of, right, there are lots of libraries that have implemented, right, extractive text summarization. Jensen is one of them that's really popular. I think a lot of you have used it. I've talked about it with a lot of you here. It's a great library, so I highly recommend that one.
Okay.
But then, in terms of how do you get into deep learning, I don't know if there's really a simple way. I know that there are lots of tools that are trying to abstract that and make it, right, like much easier to develop these deep learning models, but I'm somewhat critical of them. My biggest reason is that if you wanted deep learning, I don't think is going to get to that. No, lots of companies are trying to do that, trying to make it really easy to use and democratize it. But if you want to train these algorithms, there's just so much going on, and every data set that you introduce to these models change the way that you set these parameters. So I know that they're trying to create these algorithms that are just more generalizable, that would work for all tasks, but I just don't think that the community's there yet. And so you have to know that, right? So like some tricks like in recurrent neural networks, something that took me a while to figure out is that I didn't know that all these papers were using what's called gradient clipping. So they were actually, they had a min and max on the value of the gradient that was being reported. And so most people who were training and weren't part of like a Stanford research group were having all these issues trying to train the recurrent neural networks until someone just finally reported, hey, we're using gradient clipping. It's a hack, but this is how we propagate our gradients by making sure that they don't go under or beyond some values. And having knowledge about that, and it applies, I mean, different ones apply to different problems. So that's why I think it's a little harder, at least at this state, to find something that would just kind of do this out of the box. Or unless you wanted to just do something like you wanted, there are lots of tutorials out there that will just give you like a trained model and you can just kind of have fun with it and see. But in terms of like trying to do it yourself, I don't think that it's there yet. I think maybe other people can argue against it. I'm not familiar with like Keras. I think that's another high-level API and a lot of people have been talking about and using. So.
What entity or who or what actually now with this in machine learning?
Yeah.
For summarization. Text
yeah.
Summarization.
So I've noticed that this is no offense to lawyers, but a lot of people have been talking about like lawyers have to read lots, and they're saying that this can be some way to help them or replace them, where you could just like create these like summarizations of all these texts or just get you to like the relevant portions of a document. And because it's using the statistical properties of your corpus and just finding out based on the previous of what it's learned of what's relevant or what is generally relevant given a task, what's relevant for the future. So
they already have services now with AI to do like traffic log like in England, and that guy's monetizing it to do more for U.S. U.S. Citizens, not the traffic, but other legal matters.
Yeah.
So I just want to thank you. I appreciate it.
John, you start covering the DC deep learning work.
Well, I'm probably going to do that. Thank you. I appreciate it.
And that's it. If anyone has any last minute questions. All right.
I guess we'll do like another 5 minutes of questions if you want to answer. Are you going to stick around for drinks afterwards?
Yeah.
So we'll do like a couple, 3 questions, and then we'll take it to Dave drinks if there are some more questions. If not, thanks for coming, and we'll see you next time.
Thank you. Yeah.